All right, everybody. So let's take out our notes, and we are on the next section, 4.4.
No.
4.4. Can you put it here? Out of the way. Oh, do you need it?
Kind of, well, it'll erase once I close it, so.
Okay. All right. Huh? This is not going to be on the test. Okay, 4.4, indeterminate form and L'Hopital's rule. Okay, so the way you write this person's name is like L hospital, but you read it at like L'Hopital.
What?
It's L'Hopital.
Doesn't sound French.
I don't know if it's French, but
It doesn't sound
yeah. So it's called L'Hopital's rule. All right, let's recall this limit question from chapter 2. Okay, sorry. I don't know if you guys got that. Okay, let's recall this limit question from chapter 2. What happens if I put 1, x equals 1 in there?
It's not working.
It's not working. What happens? Not just the denominator.
Everything. It's 0 over 0.
0 over 0. We get 0 over 0. So then we said the limit does not exist. We keep going, right? Every time you get 0 over 0, you know the limit exists for the most part. And we got to do something else. What did you do in chapter 2 to solve this problem? A long time ago, I know. Huh? You did something called factoring.
Oh, yeah.
Yeah, okay. All right, so we take out x minus 1, and then we factor this. Yeah?
And we have to put limit x to 1.
Right. We have to put limit as x goes to 1. Yes. So we factor and we put limit as x goes to 1, and then we said this cancels. So limit as x goes to 1, it becomes x over x plus 1. So that whole function becomes x over x plus 1. And then what do we do now? Plug it in. So we get 1 over 2. Correct? Yes. And the only reason we do that is because it was 0 over 0, right? Okay, so I'm going to teach you a shortcut for the most part. This method works on pretty much everything that has an indeterminate form. However, sometimes the rules you learn in chapter 2 is faster. So you kind of have to judge which way is faster for you at that time. Sometimes L'Hopital's rule is actually longer than just thinking about this problem and say, oh yeah, of course, it's this number. So you don't want to just always use L'Hopital because you're like, hey, it's supposed to be faster. No, sometimes it's slower. Okay, so use your best judgment. All right, so L'Hopital's rule says if f and g are differentiable, and g prime is not 0. Okay, L'Hopital's rule. If f and g are differentiable and g prime is not 0, on open interval that contains a, except possibly at a. Okay, again, so you have two functions, f and g, and they are both differentiable, meaning you can find the derivative. And g is the one in the denominator. G prime is not 0, and we are talking about an open interval that contains a. Okay, so that means if you're trying to find the limit as x goes to a of f of x over g of x, and then you can take the derivative of f and g on its own, and g prime is not going to be 0, and the limit as x goes to a of f of x is equal to 0, and also limit as x goes to a of g of x is equal to 0. So you take the limit of each one, and both of them equal to 0. Or also, it doesn't have to always equal 0. It could also be plus minus infinity. That is also something that works. Okay, so either you get 0 over 0, infinity over infinity, or plus minus infinity over plus minus infinity. If any of those things happens, then so basically if you get the indeterminate form, 0 over 0 or infinity over infinity or plus minus version of those, then the limit as x goes to a of f of x over g of x is the same as taking the derivative and then plugging that number in. Oops. Okay, so I'm going to look at the original problem, and then we're going to do it with L'Hopital's rule.
Hold on.
Oh, yeah, of course.
It's quite a lot.
Yeah. Okay, so basically it's saying if you have this limit that you want to find, and then the numerator and the limit of the numerator, the limit of the denominator both go to 0 or both goes to infinity, then you can apply L'Hopital's rule, which says the limit is the same as the derivative of each function at that value. Okay, it's almost done. Yep.
Plus minus infinity over infinity.
Yeah. All right, let's take a look. So on this original problem, we got, so basically, the limit as x goes to 1 of the top function, which is x squared minus x, that is equal to 0, bless you, when we substitute, right? And then the limit as x goes to 1 of x squared minus 1 is also 0. So then this gives us the indeterminate form of 0 over 0. So we're going to use L'Hopital's rule. That tells us we can just take the derivative. So the derivative of the numerator gives us what? Oh, not a hard problem. What's the derivative of the numerator?
2x minus 1.
Good. 2x minus 1. So the limit as x goes to 1 of 2x minus 1. And then what's the derivative of the denominator? 2x. Okay, now we substitute. So 2 times 1 minus 1 over 2 times 1, which is 1 over 2. Okay, so we get the same answer. Whether you do factoring in the beginning, that way we learned in chapter 2, or we use L'Hopital's rule, both of them give us 1/2. Okay, but if you want to use L'Hopital's rule, if it's not a multiple choice question on the test, you have to write all that. So you have to justify why are you using L'Hopital's rule. You have to show them the limit on the top is 0, the limit on the bottom is 0, therefore I can use it. If you don't do that and you just took the derivative, you would get it wrong. Okay, on the multiple choice, it doesn't matter. As long as you choose the right answer, you're good. Okay, notes on L'Hopital's rule. I'm sorry. Okay, so you have to show limit as x goes to a of f of x equals 0, and limit as x goes to a of g of x equals to 0. So if you don't do that on the FRQ, then you're going to get it wrong. So make sure you do that. You have to show each limit is equal to 0. And also, this can also work for one-sided limits. Can work for one-sided limit. Okay, that means you can have limit as x goes to a plus and a minus, things like that. One-sided limits are also okay. All right, let's look at why L'Hopital's rule works. You guys good? Okay, so let's look at graphically. So let's say that we have two functions. One we call f, and the other one we call g. Oops. And they cross at this point, and this point we're going to call it a. So if you want to find the limit, as x goes to a of f over g, well, what's the limit as x goes to a of f? What is f of a?
0.
0. What is g of a?
0.
0. So 0 over 0 is my indeterminate form, so that tells me that I cannot find an answer, but there is a limit. Yeah?
Do we need to write this down?
Yes. Well, you don't have to write down anything I give you. It's just good information.
Well, at least the proof part.
The proof part is good to know because just in case they ask this kind of question on the test. Okay, so this part, recall, so I'm kind of like zooming in on that part, the A part. So I'm going to zoom in and say that I zoom in so much that this part looks almost like a straight line. So remember in chapter 3, local linearity, we said we zoom in so much that it pretty much looks just like a straight line. And so we can just use linear approximation and say f is equal to the slope times x minus a. So linear approximation. So saying that that line, that curvy line, when you zoom in so much, it's pretty much like a straight line with that same slope. Like almost like a straight line. And then we can say g is pretty much a straight line as well, but it's a different slope, but at that same point. So then, since we zoom in so much, we can just say, well, f over g, f is m1 over x minus a, g is m2 over x minus a, and that x minus a cancels out. You just have slope of f over slope of g. So basically, L'Hopital's rule is derived from the knowing that it's a locally linear graph, which means it has to be differentiable to be locally linear. All right, let's solve some problems. Okay, find limit as x goes to 1 of natural log x over x minus 1. Limit as x goes to 1 of natural log x over x minus 1. This one, I believe you have to use L'Hopital's rule. We can't do factoring. We can't cancel anything. We had to find the limit. Now,
Can we zoom back out to the proof?
yeah. Okay, so limit as x goes to 1 of natural log x over x minus 1. All right, so we can kind of do a mental check and say like, if I put in 1 in natural log x, what do I get? 0, and then x minus 1, so 1 minus 1 is 0. So we know it's going to be 0 over 0. Now, if you want to use the L'Hopital's rule, you got to write it all out. So limit as x goes to 1 of natural log x is 0. Limit as x goes to 1 of x minus 1 is 0. So basically, I'm finding the limit of the numerator and the denominator. Okay, now, we want to use the L'Hopital's rule, so we put L'Hopital here. And then, so we take the derivative of the top. What is the derivative of natural log x? 1 over x. 1 over x. What is the derivative of x minus 1? 1. Okay, so the limit as x goes to 1, which is 1 over 1, so 1. The answer is 1. Okay, So limit as x goes to 1 of natural log x over x minus 1. Without graphing it, you can't tell what the limit is. So what we want to do is use L'Hopital's rules. But before that, you have to show that you can by finding the limit of the top and the bottom on its own. Now that you show that it's 0 over 0, you say, I'm going to use L'Hopital's rule, take the derivative, and then put that number in there. Good? Yes? Okay, let's try 1. Okay, number 1. Limit as x goes to infinity, natural log x over square root x. Okay, go ahead and do that one, and then we'll go over it together. Okay, if you want to use the L'Hopital's rule, remember you have to show that you can. So you gotta show the limit for top and bottom separately. Okay, so this question, limit as x goes to infinity of natural log x is infinity, and limit as x goes to infinity of square root x is also infinity. So we can use L'Hopital's rule. Okay, that means we need to take the derivative of the top and bottom separately, okay? So the limit as x goes to infinity of 1 over x over 1 over 2 square root x. Okay, and then we want to simplify that. We get 1 over x times 2 root x. So we are looking for the limit as x goes to infinity of 2 square root x over x. Now, if you put an infinity at this point, you still get infinity over infinity, so it doesn't really help us unless you try to simplify that a little more. And basically, square root x is x to the 1/2, and you have an x on the in the denominator. So this is limit as x goes to infinity of 2 over square root x. Now, if you plug in infinity at this point, you get 2 over infinity, which is 0. So the answer is 0. However, this problem, yeah, I guess this problem you probably have to do it this way. But, yes?
So you can't cross out infinities? So like at the 2 times square root x over x, you can't cross out.
No, because the thing is, the question is which infinity is bigger? Is this infinity bigger than this infinity? You don't know, so. So the thing is, this question, you really don't have to use L'Hopital's rule. If you remember chapter 2, we just said dominance, right? Which one is going faster? Natural log is like this graph, and square root x is this graph, right? So square root x is a lot bigger than natural log x, so eventually it's going to be 0. So this question is much faster without L'Hopital's rule. But of course, you can use both.
Should we say just on solving like that?
If you had to explain, yeah, you can say the degree is
Greater than.
yeah. Okay, let's try number 3. This one goes to 0. If you plug in 0, what do you get? Natural log 0 is what?
Negative infinity.
Negative infinity. It doesn't exist, right? It keeps going down. What's 0 minus 1? Negative 1. So you get infinity or negative infinity over negative 1. Can you use L'Hopital's rule? No, please don't use L'Hopital's rule whenever you think we're in that section. You have to check if it applies. So does it apply? No, we cannot. So what's the answer?
Infinity.
Yes. Remember, only 0 over 0 or infinity over infinity is L'Hopital's rule. Other than that, if you get 0 over infinity or infinity over 0, well, actually, what is 0 over infinity? 0, right? 0 divided by a very large number is just 0. What is infinity over 0?
Does not exist.
Does not exist. Okay, so not everything is indeterminate. All right? All right, we have time for one more. Let's try a sine and cosine problem. Okay, this one, you have to start with L'Hopital's rule, but then once you take L'Hopital's rule, you have to actually do it 3 more times if you want to use L'Hopital's rule all the way until the end. So it's much easier if you just use things we learned before. Okay, so first step, you do have to use L'Hopital's rule, but the second step and beyond, you don't have to use L'Hopital's rule. Okay, try that one. All right, for the sake of time, let me just kind of show you. So basically, this one, you're going to use L'Hopital. And then you get secant squared x minus 1 over 3x squared. If you put in 0 right now, you're still going to get 0 over 0. Oh my gosh. Okay, sorry, give me 1 sec. So secant squared minus 1 is tangent squared. 1 plus tangent squared equals secant squared. Okay, this is tangent squared is sine squared over cosine squared, right? Remember, this is the limit as x goes to 0, so this thing goes to 0, goes to 1. Remember that rule? Limit as x goes to 0 of sine x over x is equal to 1. Much easier this way. So that's going to be 1, and a cosine square of 0 is 1, so the answer is 1/3. Or else you have to take L'Hopital's rule 2 more times, and that's going to take too long. Because you need to reduce it so that it never gets 0 over 0 again.
So do we need to write L'Hopital like every time? Like do we need to prove that we can use L'Hopital every time?
If you want to use it, yes.
So we need to write like 3 more times?
Yes, if you want to use L'Hopital all the way, yeah.
Why don't we give it cosine square?
Because cosine of 1, cosine of 0 is 1.
Oh, okay.